Welcome back to Math 110, Intro to Number Theory. And in this lecture video, we're going to finally talk about quadratic reciprocity, which we were building up to in the previous video about Gauss's lemma. So first, let's recall some properties to remotivate one reason why we might care about this quadratic reciprocity law. And so the Legendre symbol has the property that it is completely multiplicative, meaning that if the top of the symbol is it factorizes, then we can turn the Legendre symbol into the Legendre symbol of a product into a product of Legendre symbols. And we also, using Gauss's lemma, came up with a simple condition for when 2 is a quadratic residue mod p. And that was if p is 1 or 7 mod 8, then 2 is a quadratic residue. And if it's 3 or 5 mod 8, so the other case, then it's not a quadratic residue. So the problem of assuming that we can factor things easily, calculating Legendre symbols reduces to the problem of calculating these Legendre symbols where both the top and the bottom are odd primes. So now, given that that is what it reduces to, the next step is, I guess, trying to understand those. And the quadratic reciprocity law is that whether Q is a quadratic residue mod P is intimately related to whether P is a quadratic residue mod Q. So they have this reciprocation relationship. And it's almost that it's perfectly reciprocal, but there is this multiplicative factor in here that negates it sometimes. So if either P or Q is 1 mod 4, then it's perfectly reciprocal, and otherwise it's the negation. So when P and Q are both 3 mod 4, then Q is a quadratic residue mod P if and only if P is not a quadratic residue mod Q. Okay, so the way that this lecture will go, this video, is that we're going to go through this lemma that shows up, that gives a result that we need right at the end. Then we'll go through the proof of quadratic reciprocity, which actually isn't that long, but it does feel a little random. And then we'll give some example, and then that'll be it. I should say quadratic reciprocity is actually a very deep thing, and there's just like a lot of math that's been developed over the intervening years since Gauss first studied it. But that would take us way too far afield. So, okay, let's look at this first lemma. So if P and Q are odd primes that are not equal, then there's this relationship between sum of sums of floors and a product. And this product you should recognize as being the top of the exponent in the quadratic reciprocity law. Okay, and so it's the sum of over k of k times q over p floor, and then it's the same sum but with q and p reversed. The proof for this is fairly geometric. So just to start things off, we're going to be looking at the line y equals q over p times x, and we'll see how that comes in. But first, so this theorem ends up being about counting how many lattice points there are in a particular region and decomposing it into 2 triangles and adding it up. And this line will be the boundary between those, which is roughly indicated here. And since P and Q are both distinct primes, there's a special property that happens with this. So the question is, what lattice points lie on this line? And a lattice point is a point where both x and y are integers. If both x and y are integers, then, well, sure, y is an integer, so that means that q over p times x is an integer. For that to be an integer, though, that means that p divides q times x. But since p and q are distinct primes, p must be dividing x, and that's also sufficient for it to be an integer. So p dividing x is exactly the condition for there to be a lattice point on this line. So, okay, so S. Let's set S to be the subset of the natural number lattice, where x is in the interval from 1 to p minus 1 over 2, and y is from 1 to q minus 1 over 2. So how many lattice points are in here? So for that, we can, because x and y are independent in some way, we can take, it's forming this rectangle that's p minus 1 over 2 points wide and q minus 1 over 2 points tall. So the number of points in S is the product of those two numbers, which happens to be the right-hand side there. Okay, now using this line, let's decompose S into a union of all those points x, y, where y is less than or equal to q over p times x, and then the same set but with a greater than or equal to. So what points do these sets have in common, if any? So if they did have a point in common, then that would be a point that lies on the line, which is why we considered this earlier. And so then p would divide x. But if p divides x, well, in that there's this condition here, which is that x is between 1 and p minus 1 over 2. So, well, since p is prime, well, actually, no, just because it's in this range, there's no way that p divides x. So that means that they have no points in common, and in fact, these are disjoint. Okay, so the next thing is I want to take all the inequalities involved and then rewrite the sets in a way that will be useful. So the first set I'll take as the points x, y, where x lies in the range that's given, and y, well, y is greater than or equal to 1, that's given, and also it's less than or equal to q over px. And I'm tossing out this part. And the reason for that is, well, how big can y be according to these two inequalities? So y is going to be less than or equal to q over p times however big x can be, which is p minus 1 over 2. And then bringing the q minus p into the numerator, we have a q minus q minus some positive number over 2. And so the fact is that since q is odd, we're subtracting some number from it and dividing by 2, if we took the floor of this, then it's going to be less than or equal to q minus 1 over 2. Because we're going to have to round this thing down, or round it up at least to 1. For this to even be an integer. And we're taking the floor because that's the largest y can possibly be, because it's an integer, is the floor of that fraction. Okay, so that means that we can just ignore this inequality and write it simply as this pair of intervals. And similarly, swapping x's, y's, p's, and q's, we can manipulate the second one. So, because okay, so the cardinality of S then, because the sets are disjoint, is the sum of the cardinalities of the two sets. And then I'm writing this set as a bunch of slivers and summing up those cardinalities instead. So for each possible value of x, I can sum up the cardinality of just the points with that value of x, and I can also then drop x off the representation of it because I'm just counting. So okay, with the first set, I am taking all the points under the line and taking vertical slices for each x. And then for the second set, I'm taking the same thing, but horizontal slices for each y. Now the thing is, this set of the size of the slice, all the points that are between 1 and whatever this is inclusive, what we can do, like in general, if you have less than or equal to, what you can do is take the floor of the top minus the floor of the bottom, add 1. The add 1 is so that you don't accidentally make a, it's an off by 1 error if you don't. So 1, its floor is just itself. So if we subtract 1 then add 1, that we didn't need to do that. So we just need to take the floor of the top to get the cardinality here. Because that's the largest y can possibly be. So we do the same for both. And, well, what do we have? We have the left-hand side of the sum, except with x's and y's instead of k's and l's. Okay, so that was that lemma about dissecting a rectangle and counting lattice points. And now it's time for quadratic reciprocity, the proof. So let's suppose p and q are odd primes, and just the trivial case p equals q, then it just happens to be satisfied because both of the Legendre symbols are 0 in that case. So let's assume p is not q. So just like in the proof of Gauss's lemma, for studying whether q is a quadratic quadratic residue, we take the arithmetic progression starting from q, and recall that if we take the the mod p absolute value, which we introduced in that proof, and it's just a one-off notation thing for these, so yeah, don't use it outside of these proofs. So okay, what was it defined to be again? And here's a better proof than in the previous video, or a better definition than in the previous video. If you want to calculate the mod p absolute value of x, then what you do is you find an x prime that is congruent to x, that's centered at, or in the interval centered at 0. So from minus p minus 1 over 2 to p minus 1 over 2. And then we take the absolute value of x prime. So this gives us a number that's from 0 to p minus 1 over 2. So recall that the set of these mod p absolute values is a permutation of 1 through p minus 1 over 2. So what that means is that if we were to, well, in the previous one we multiplied all these absolute values together, but this time let's add them all together. And if we do so, then it's the sum of all the numbers 1 through p minus 1 over 2. So we'll just write that as sigma notation. Okay, so the next thing is we want to then sum up the actual arithmetic progression and try to relate it to these other things. So on one hand, the sum of the arithmetic progression, we can pull the q out. That's something we can do. But on the other hand, we can take the kq and apply the division algorithm after dividing by q. So that gives us this representation of the quotient, which is the floor of kq over p times p, plus the remainder, kq mod p. So then for some notation, let's have S of AB be the sum for k equals 1 through, well, we want it to be the thing that shows up in the previous lemma. So, and in particular, that after we distribute the sigma over the plus and also pull the plus out, then SPQ is the thing that we get. So then also we have the sum of the KQ mod p's. So we want to understand this part a bit better now. So just like in the proof, or in the statement of the Gauss lemma, let's have mu be the number of those KQ that are negative. So in the previous video, negative meant the congruent to a negative number in that set R. And also, like here we can say it's when the absolute value is not congruent to KQ. Okay, so let's take the sum, and inside of it we'll take just the KQs that are negative with respect to this definition here. So so if we take, for example, this sum and subtract n, then we're just left with the positive ones, the ones where they're congruent to their own absolute values. So what we do now is we realize that if we have a negative one, then we can compute the absolute value by taking p and then subtracting KQ mod p. So because well, you know, that's how it works. You can check it. Okay, so that means that if we take, so we can add a, did I make it? Okay, so if we take KQ mod p and sum it all up, then we can look at the sum over just the absolute values. And then for all the negative ones, we can try to add something to it to then convert it into being just the KQ mod p. So if we add 2n minus mu p, what that does is it subtracts. So for each negative one, we're subtracting a p, which cancels this p out, and then we're adding 2n, which then not only cancels this out, but then adds it back in to make it positive. So then for the negative ones, the absolute values are turned into this form, and for the positive ones, they are already in this form. So we get this equality. And then, using our observation that it's just a permutation, then we can say that the sum over KQ mod p is the sum over k, but then plus this correction factor, 2n minus mu p. Okay, so coming back, we have that q times the sum over k is p times sq, and then we replace this using this, what we just calculated, and then we rearrange, so we subtract this from both sides and to get the q minus 1 there, and then we bring we bring the p's together there to get it in this form. And now this is actually all we need. The key here is that 2n is even, q minus 1 is even, p is odd, so therefore this difference is even. And so, since that difference is even, what that means is that if we take minus 1 to the power of it, we get 1, but also minus 1 to the power of SPQ is then equal to minus 1 to the power of mu. So all that work to get that. And that's really good because we know what minus 1 to the mu is. By Gauss's lemma, it is the Legendre symbol QP. Okay, so now doing a Harry Potter-like spell mutatis mutandis, which means change what needs to be changed. Nothing in this depended on which one was Q or P, so we can just take the proof, swap the P's and Q's, and and similarly prove that minus 1 to the SQP is the Legendre symbol for PQ. So then multiplying these two together, we get that minus 1 to the sum of the s's is the product of these Legendre symbols. And then, by the lemma that we just went over, minus 1 to the, or the sum of these s's is the product of p minus 1 over 2 and q minus 1 over 2. So, we have this equality. And then the last thing is just to realize that because p and q are both distinct odd primes, that these Legendre symbols are non-zero. So we can just divide, bring one side, well, they're both 1 or minus 1. So we can, dividing and multiplying are kind of the same thing for them. So we can just bring one to the other side. And then that's quadratic reciprocity. Though it is also commonly written in this form. It's nice and symmetric that way. Okay, so that's quadratic reciprocity. Just some, I guess it is kind of hard to say why it's true. Other theorems, you do them and you have a good idea of what just happened. So, just as an example to close things off, let's look at some Mersenne primes and show that 3 is a quadratic non-residue for every Mersenne prime greater than 3. So one thing that we'll need is that, mod 4, okay, so if 2 to the p minus 1 is greater than 3, that means p has to be 2 or more. In fact, it has to be 2 or more if it's greater than or equal to 3. But because it's mod 4, that means that 2 to the p is going to be 0. And so the Mersenne prime is minus 1 mod 4, which is 3 mod 4. So that means if we apply quadratic reciprocity, because both 3 is 3 mod 4 and the Mersenne prime is 3 mod 4, then we gain a minus sign when we flip it. So now that we've flipped it, we can reduce the numerator mod 3 because it doesn't change whether, it doesn't change the Legendre symbol, its value. So notice that mod 3, 2 to the p is minus 1 to the p, and since the Mersenne prime is bigger than 3, p is not 2, so p is an odd prime, and minus 1 to the odd is minus 1. So we can calculate then that the Mersenne prime mod 3 is 1. So the symbol reduces to just negative 1, 3. And 1, of course, is a square mod 3, so this Legendre symbol evaluates to 1, and so we're left with minus 1. So we can conclude that 3 is a quadratic non-residue for all Mersenne primes. Okay, so that is the end of this series of lecture videos about quadratic reciprocity. The next lecture will almost surely be in person, and I'll see you next time.